By Deepak Chopra, M.D. and Joel Primack, the universe is filled with mystery and intrigue. But with the evolution of science, researchers are understanding more and more each year. This interview explores the Big Bang Theory, dark energy, and even how consciousness plays a role in science. Deepak Chopra, how did the universe begin? Joel Primack, we have detailed information about the Big Bang. The universe began in a very hot, dense state. About 400,000 years after the beginning, the universe had cooled enough that atoms formed, and that's when the heat radiation of the Big Bang was released, what we call the cosmic background radiation. It comes from every direction around us. We have studied it in detail and it confirms the predictions of the modern theory in amazing detail. Deepak, do we know the cause, what triggered the Big Bang? Joel, there's a hypothesis, called cosmic inflation, that very neatly describes how the Big Bang started, what put the bang in the Big Bang and made the universe expand so rapidly, and what produced the energy and matter. Cosmic inflation makes many predictions, and every prediction that's been tested has turned out to be right. So most cosmologists, physicists and astronomers who study the whole universe, think that cosmic inflation must be pretty close to the truth. Of course, the question then is, what happened before that? There's a theory called eternal inflation, and cosmic inflation would just be the last moment of eternal inflation in our part of the universe. But we have not yet been able to test eternal inflation. Deepak, is cosmic inflation the beginning of the Big Bang, or before the Big Bang? Was there a Planck epoch? Joel, if eternal inflation preceded cosmic inflation, there probably never was a Planck epoch. Eternal inflation would operate at very high energies, but lower than the highest energy possible, the Planck energy. Deepak, was there never a beginning then? Joel, it's a controversial question. There was a paper that claimed to prove that eternal inflation must have started a finite time ago, so it's only eternal in the future, not the past. But a loophole was found in that paper, so the answer is not clear. The farther back you go, the hazier it gets. Deepak, in cosmic inflation, the universe triples in size every tiny unit of time, and triples again and again, and then this exponential expansion stops and the universe expands much more slowly. Do we know the mechanism of that? Joel, cosmic inflation is really the name of a class of theories. In such theories, cosmic inflation ends quickly and converts to cosmic expansion. Many such theories all make similar predictions that seem compatible with the universe we observe. The details can, in principle, be worked out with enough data, and we're beginning to obtain such data. There was a claim that the BiCep experiment had seen evidence of gravity waves from the cosmic inflation era. But the BiCep group then worked together with the European Planck satellite team, and their revised conclusion was that their original paper was mistaken. The region of the sky that BiCep looked at from the South Pole was contaminated by dust in our own Milky Way galaxy, and what they saw was almost certainly the dust signal. That team and other teams are doing much more precise experiments at several wavelengths that will allow them to disentangle the effects of dust and other foregrounds, so over the next few years we are going to know the answer. If it turns out that we can see the gravity waves from cosmic inflation, we will be able to reconstruct what happened. This would allow us to get close to the Planck scale, the highest energies and smallest things allowed by physics, a very exciting possibility. Deepak, in your book, The View from the Center of the Universe, you say that the Big Bang occurred everywhere. Please explain that. Joel, the entire visible universe was a small region at the time of the Big Bang, and the stuff that would become our galaxy and us was deep inside it. The early stage was very simple and smooth, with only small differences in the density of matter and energy in different regions, about 30 parts per million more here, and about 30 parts per million less there. But that was enough to cause tremendous differences later. Galaxies formed here, no galaxies form there. And in the observed universe we really do see such big cosmic voids with very few galaxies. Deepak, where did the energy come from for the Big Bang? Joel, almost all the energy during cosmic inflation was in a quantum field called the inflaton. If such a field isn't at its lowest energy state, it will automatically cause the exponentially rapid expansion of cosmic inflation. But the process also has to end very quickly as the inflaton's energy gets converted to the energy and matter of the universe. Deepak, what happens then? Joel, actually, we know a lot about things that happen starting about a millionth of a second after the Big Bang, since physicists have explored the relevant processes in the laboratory. In 1977, Steven Weinberg wrote a wonderful book called The First 3 Minutes, it's actually more like 10 minutes, describing how most of the light elements were formed at that early era. The deuterium, heavy hydrogen, and most of the helium were formed then, and the theory predicted just how much of these light elements get formed. We've now been able to measure precisely the amount of deuterium and fairly precisely the amount of helium, and the good agreement with theory is impressive. However, there may be a disagreement between theory and observation for the next lightest element, lithium. Deepak, is this evidence that if the values of the fundamental and cosmological parameters were any different, we couldn't be here? Joel, yes, but it's a little more complicated. There was a period when physicists were quite excited about these so-called anthropic arguments, which have to do with the universe being fine-tuned so that creatures like us can exist. The way they played that game was they kept all the constants of nature the same except for one, and showed that if you just changed that one even a little bit from what we measure it to be, our universe and creatures like us couldn't exist. However, if you are allowed to change more than one constant at a time, then it turns out that creatures like us, carbon-based life, could exist in very different sorts of universes. Deepak, how did galaxies come into existence? Joel, quantum effects during cosmic inflation create the slight differences in density from place to place that make galaxies form in some places and not in others. These quantum fluctuations are on microscopic scales, but they get blown up to astronomical scales by the tremendous expansion during cosmic inflation. Regions that start slightly denser than average expand a little slower, gravity slows them down. Regions that start out slightly less dense than average expand a little faster. Astronomers call regions of higher density richer and regions of lower density poorer. Gravity makes richer regions richer and poorer regions poorer. There are never any exceptions, that's why it's the ultimate Scrooge principle. Richer regions are where galaxies will ultimately form. Poor regions grow into big cosmic voids where hardly any galaxies form. And so the structure of the universe that we see today has most of the galaxies in sheets surrounding the big cosmic voids, and the galaxies tend to lie along lines that we call filaments. The distribution of the galaxies in space agrees remarkably well with the theoretical predictions. Deepak, and now we have a situation where 70% of the universe is dark energy, 25% or so is dark matter, and only about 5% is the sort of stuff that atoms are made of. What is dark energy? Joel, we wish we knew. We don't know what dark energy is. We don't even know why it's there, or what role it played in the early universe. But now it's making the universe expand faster and faster. Effectively, dark energy makes space repel space. Deepak, this expansion, I'm told, is faster than the speed of light. Joel, rather, what's happening is that the whole universe is expanding. If you are on an expanding racetrack, if you look farther and farther away, things will be moving away from you faster and faster just because they are farther along the expanding racetrack. At a certain distance, galaxies will be moving away from you faster than the speed of light. This doesn't contradict relativity, it's what relativity predicts. Deepak, so this explains how the most distant objects in the visible universe are about 47 billion light-years away even though the universe is less than 14 billion years old. Joel, yes. Deepak, what is the 25 or 26% that we call dark matter? Joel, I proposed back in 1982, with the late Heinz Pagels, that the modern theory of supersymmetry gives us a natural candidate for the dark matter. Supersymmetry is probably the best idea. We have to go beyond our standard model of particle physics, and supersymmetry is the basis of string theory. If supersymmetry is right, all the fundamental particles we know, the electron, quarks, the photon, and so on, have superpartner particles that we haven't discovered yet. The superpartner particles must be much heavier. And they have funny names: squarks, the partners of the quarks, sleptons, the partners of the leptons, photino, the partner of the photon, the lightest of these particles, perhaps the photino, might be the dark matter. Deepak, is it true that the dark matter is not atomic? Joel, yes, the dark matter has nothing to do with protons, neutrons, or electrons, the stuff that atoms are made of. Deepak, it doesn't absorb light or emit light. Joel, not to any great extent. Deepak, we are made up of atoms, right? Joel, yes. In fact, we're mostly made of a very special kind of atom, not the kind that came out of the Big Bang, except for hydrogen, but rather atoms that formed in stars. Deepak, so how do we interact with something that's not made of what we're made of? Joel, a good example is neutrinos. To solve a mystery and avoid a catastrophe in physics, the breaking of fundamental laws like conservation of angular momentum and energy, Wolfgang Pauli suggested that there's a new particle, subsequently named the neutrino by Enrico Fermi. Pauli was very diffident about this proposal because he thought he was proposing something that could not be tested. But now we have measured many properties of neutrinos. We've discovered 3 different kinds of neutrinos and that they can turn into each other. We understand a great deal about neutrinos. Deepak, are they observable? Joel, absolutely. We can do experiments about neutrinos. Deepak, how is something observable if it's not atomic? Joel, well, neutrinos are weird. They only have weak interactions. Their masses are so small that their gravitational interactions are essentially negligible. Deepak, can dark matter be of the same category? Joel, yes, except that dark matter has a great deal of mass. If dark matter is the lightest superpartner, it is a weakly interacting massive particle, a WIMP. Then it would interact with ordinary matter like neutrinos. But since it would be very massive, in fact, it would be most of the mass of the universe, it would have a great deal of gravity. So it's a combination of those two ideas. Deepak, so we're now in a situation where 95% of the universe is invisible? Joel, correct. Deepak, it's at the moment unknown, possibly even unknowable. And about 5% is atomic matter. Joel, yes, mostly hydrogen and helium that came out of the Big Bang. The heavier elements, which we and the Earth are mostly made of, are only about 0.01% of the cosmic density. Deepak, the atomic matter has the particle-like thingness about them, but they are also waves that can't be localized. Joel, no, waves can be localized, with greater or less precision. The better you know their location, the worse you can know their momentum. If you want to localize it in time, then you know less about its energy. These are the uncertainty relations of quantum mechanics. Quantum mechanics is the best tested theory in all of science. Deepak, but do we really understand quantum mechanics? There are so many interpretations. Joel, yes, the old Niels Bohr interpretation is often paraphrased: shut up and calculate. The theory makes very precise predictions that we can calculate. There's no dispute about the calculations. The problem is that if you try to describe what's going on in ordinary terms, there are many different kinds of language that you can apply that sound very different, but that don't seem to have any different implications. Deepak, it works, but what does it mean? We don't know what caused the Big Bang. As Sir Arthur Eddington said, something unknown is doing we don't know what. On the one hand, experiments verify the theories, and yet what's going on? Joel, I don't think we should be surprised at the growth of mystery with the growth of knowledge. Newton is supposed to have said that to himself. He was like a young child at the seashore, every so often picking up a particularly beautiful stone or shell, while he looked out at the great ocean of ignorance before him. We live in an island of scientific understanding. As we learn more, the island grows, but so does the size of the shoreline where ignorance meets knowledge. Deepak, so science has expanded the mystery of existence? Joel, precisely. And we shouldn't be surprised at that. The more we learn, the more questions we ask. It doesn't look like science will end. It's hard to conceive of an ending caused by a lack of interesting questions. The questions we can ask now are very different questions. We didn't know there was dark matter or dark energy before. Now we know, And of course we want to know what they are. We have a very elaborate program to try to answer those questions. For example, experiments deep underground, to protect from cosmic rays, may detect the dark matter particles. The U.S. is going to increase the sensitivity of our most sensitive experiment by a factor of 100. If that experiment doesn't discover WIMPs, it could rule the theory out. But it may discover WIMPs. There is also evidence from the Fermi gamma-ray satellite that may indicate that dark matter is annihilating itself in the center of our Milky Way galaxy. The evidence is tantalizing, but it isn't convincing yet. A lot of other data may materialize in the next few years. We might be on the threshold of making a great discovery, but I don't know what the answer is going to be. No one knows yet. Deepak, I want to bring up the element of consciousness. In your book you say that we need sentience to know this. I was reading Freeman Dyson's book, Infinite in All Directions, where he suggests that there is sentience at all levels from the atomic to the cosmic level. I was in a debate with our friend Richard Dawkins, and I quoted Dyson. He screamed at me that Dyson never said that. The sentence I quoted is that every experiment forces the atom to make a choice. I wrote to Dyson, and he responded that there are three riddles that have confounded him all his life: the unpredictable movement of atoms, a universe fine-tuned for mind and life, and our own consciousness. They seem to have some connection to each other. Any comment on that? Joel laughs. Freeman Dyson has written many essays over the years. The first collection was called Disturbing the Universe, that are of wonderful insights, wisdom, and questions. Dyson also wrote the first article that discussed in detail the distant future of a universe that goes on forever. These are great mysteries, and I think they are going to keep us busy for a very long time, both scientifically and philosophically. I don't expect to have easy answers to any of them. Deepak, is science a product of consciousness? Joel, of course. And the connection between mind and brain is a fascinating mystery. My father-in-law had a stroke, which drastically changed his consciousness, so there is clearly a connection. You are an expert on these things from your medical education and practice. Deepak, are mind and brain the same thing? Joel, I don't think so. Deepak, then you are a dualist? Joel, not exactly. What's going on in my mind was drastically influenced by what happened in other people's minds throughout history. The language I use is not something I invented, it's something I learned. It's a cultural creation. We're interacting not just on the level of the words, but also in other ways. You smile, and I have a warm feeling. It's visceral. We know that the brain has these tight connections to the heart, stomach, and so on. To imagine that it's all in one's head is crazy. Deepak, if we are non-dualists, we have to ask if the fundamental reality of the universe is physical or non-physical. Or don't those words mean anything? Joel, the trouble with the word physical is that most people think of chairs and tables and things like that, which are solid. But we now know that's just a macroscopic description that has little to do with how these things look on the microscopic level. We can now see individual atoms. We know how things work on the atomic level, and it's very, very different. Calling something physical, if it invokes this common sense meaning, is very misleading. Deepak, is there a fundamental ground to reality? Joel, as far as we know, quantum mechanics is pretty fundamental. But at some level there is a conflict between quantum theory, which describes how things work on the level of the very small, and general relativity, our theory of space, time, and gravity, until we have an encompassing theory that explains how they fit together, and also how to extrapolate beyond their individual domains of validity. We won't know how far we can trust either quantum mechanics or general relativity. Deepak, what's your prediction of where science is going to take us in the next few years? Joel, I think we're going to learn wonderful new things about how the universe evolved and how galaxies formed. We're still in the process of writing papers about some fascinating discoveries from the biggest project in the history of Hubble Space Telescope. I think we're going to discover the dark matter, or else rule out current theories. We may discover a great deal about the nature of dark energy. We have a bunch of new telescopes on the way and wonderful new projects that are underway or about to start. I think the next decade or so is going to be a phenomenal period of discovery. Deepak, is the mystery of existence going to expand? Joel, yes. Suppose we find out what the dark matter is, and it's some kind of elementary particle. It has to be something completely different from everything we know, so it will be the beginning of the exploration of a whole new world. I don't foresee an end to this exploration anytime soon. Let's block ads. Why?